Okay, so yesterday we had a look at how a linear spring functions, and we saw that the PV diagram is a linear one. So let's just try to wrap up the remaining of what is there in chapter 4. And okay, pen sensitivity is a bit too low, so let me just adjust it real quick. Yeah, this is better. So now let's come to a small concept where you have work done against vacuum. Okay, so work done against vacuum is a very common situation in many processes, because on the one hand you have a chamber like this, and there is a partition, suppose, and you have some gas over here while the other side is evacuated, so it's vacuum. So when you sort of rupture this membrane or open this valve suddenly, so the question is how much work is being done by the gas. Now if you look at the system holistically, if you try to draw a control volume like this, obviously there has been no boundary work, there is no displacement work. But if you were to solely consider the gas as the control volume, or the control mass in this case, so when you rupture the membrane, the gas fills vacuum. So the process of the gas filling the vacuum happens very quick. So it's not a quasi static process, and it's definitely a process where the back pressure is zero, because vacuum means the pressure is zero. So in such cases you will safely assume that the work done by the gas is zero. Okay, all right, so this is just a small thing that I wanted to mention. Now let's move on to heat.
Excuse me, sir. Sir,
Yeah,
can you repeat once it?
uh, this whole thing.
Actually, I didn't understand like how the word done is zero.
So
Like
it's
actually,
like, when you if you consider the control mass, suppose this is the gas and this gas is expanding, but during expansion it has literally nothing to keep it held together. The surroundings are at P equal to 0 because it's at vacuum. Okay, so if there is no back pressure, the gas will simply expand because of its own pressure, and when it simply expands, it has to do no work. After rupturing, the gas will occupy the entire volume, but because it's a non-steady, non-quasi-static process, it does it so quickly that during the expansion of the gas to fill the entire volume, there is no back pressure that the gas sees in order to do work. So the back pressure in these particular cases, so in this case the back pressure is due to atmospheric pressure and the presence of the spring. In this case the back pressure is because of the weights put on the piston. Over here there is nothing, and hence the work done in such a case will be considered to be zero. And I'm saying it will be considered to be zero because there is no true vacuum. So I'm writing here P equal to 0, but in reality it is P approximately equal to 0. Because any vacuum pump will, I mean, no vacuum pump will take you to true vacuum. So it will be maybe 1 millitorr, the pressures are something like this, or tens of millitorr. So they are very small compared to, say, what the pressure of the gas is. Okay. That is why we say that the work is assumed to be zero. There will be a very small amount of work done, but it can be neglected.
yes, sir.
All right. So now let us move on to the definition of heat. So the definition of heat is not exactly what we use in daily language, and I mean, you sort of know that yes, heat is being transferred, but like again, as I had already mentioned in the previous class, heat is not held by a system. Heat is something which is in transit. So heat is the form of energy that is transferred across the boundary of a system. But apart from something which is being transferred at the boundary of a system, another useful distinction between heat and work is that you need a hot system and you need a cold system. And spontaneously, heat will be transferred between the hot system and cold system. So this is like the system boundary. Okay, so the different terms that we will encounter are Q, that is the total amount of heat transferred, specific heat, which is Q over the mass, and the same, I mean, specific quantity is per unit mass. And heat transfer can be, is affected by, first of all, the difference in the two temperatures. Not only that, heat transfer depends on the gradient of a temperature field. And this is something which you will learn in your heat transfer course. Okay, so it depends on the gradient of temperature or the negative of the gradient of temperature, and this is something which is termed as the Fourier law. The same guy who made the Fourier series. And for the purpose of this particular course, we are not dealing with the microscopic description of heat transfer and temperature distribution, but we will deal with a macroscopic distribution where you say that yes, you have a chunk of hot system and then you are transferring heat to a cold system. But the microscopic study, it will say that even in this hot system, how is the temperature distribution seen? For example, this region will be relatively cold, this region will be relatively hot because heat is being transferred from this point. So you expect that this region will be slightly colder than this. So it's like saying you have a processor. So this is the processor on your motherboard, and you have a heat sink, and the heat sink, it has many such aluminum fins. It has a lot of fins on top. Has anyone ever seen the heat sink? I think you have, because in one of the classes someone answered heat sink.
Yes, sir.
So these are the aluminum heat sinks. And so what happens if you look at the cross section, these are the fins. This is the base. I mean, I'm crudely drawing it, and this is where the hottest point will be. That is the contact with the processor, and heat is transferred to air at maybe 30 degrees Celsius. So this may be 70 degrees Celsius and this 30 degrees. So the microscopic study of heat transfer will tell you that the distribution of temperature is like maybe 60 degree over here, then 50 degree over here, then 40 over here, and finally the tip becomes 30 degree. Okay, this is how the temperature distribution will be: 50 degree, 40 degree. But the macroscopic study that we are trying to do, we will consider this as a mass at a certain temperature, at a certain average temperature. Okay, so it may not be 70, so maybe the average temperature is maybe 65 degrees Celsius. So we will deal with such kinds of average quantities. We will not consider the microscopic distribution of temperature inside the systems unless otherwise specified. Okay, all right. So uh, we've come to the end of chapter 4, and now we will do a few problems before we move on to the first law. First law for a closed system, that is. So problems. Problem. So let's do problem. So let's first do the example problem, because then you can also look it up in the book. And yesterday someone pointed out that okay, we have done already the spring problem. If you recall, we've done the spring problem yesterday, and someone said that what if we have these stops instead of having a spring? What if we have stops in the system? So let's see, let's draw such a system and let's try to solve such a system. So this is the cylinder, and the cylinder is open to atmosphere like this. We will draw a piston, something like this, and we will draw stops. This is one stop, this is another stop, and this entire region, is filled with water. Okay, this entire region is filled with water. All right. Come on. So the question says, so this is example 4.4 of Sontag. So the question says that such a piston cylinder arrangement, it contains 0.1 kg water. Okay, and the initial state is 500 degrees Celsius and 1000 kilopascal. So water, then the second state is the water is then cooled and there is a constant force on the piston until it reaches half the initial volume. So point 2 is reaches half the initial volume. Okay, then after that it is said that after this it cools to 25 degrees Celsius. It cools to 25 degrees Celsius while the piston is against the stops. So it is said that at 25 degrees Celsius, no, so it is not known to us whether it just reaches the stops. So we know from the problem, it it cools to 25 degrees Celsius while being on the stops. Okay, this is what we know. So the question is, find P3 W of the entire process, that is the work done in the entire process, and show the process in the PV diagram. This is very important. Okay, we must show the process in the PV diagram. So what is the, I mean, okay, let us try to draw some different scenarios. You have P over here, you have V over here. All right, so initial state, maybe it is somewhere over here. So state 1 is maybe, this looks like it would be superheated. Say this is superheated. Now process 1 to 2 is where it reaches half the volume. So what do we have? We have this initial specific volume. Say the specific volume is V1 and it reaches half the volume. Now look, the amount of mass of water that is contained in the piston cylinder arrangement is not going to change. It is not going to change. So when you say that something makes the volume go half, what happens to the specific volume?
It also goes half.
It also goes half. What happens to V2? So we can say that V2 is half of V1. So it goes somewhere over here. So this is point 2. And why have I drawn it on a straight line?
Constant force.
Because there is a constant force. Very good. So because there is a constant force, the pressure is going to be the same as the initial pressure. And can I pinpoint where this point is? Can I pinpoint this point?
Yes, sir.
So this point is at 1000 kilopascal and 500 degrees Celsius. So the 500 degrees Celsius isotherm, maybe it passes like this. Okay, the intersection of the 500 degrees Celsius isotherm in the PV diagram looks something like this. Okay, so this is point 1, this is point 2, and so because we have the temperature and pressure, we are in a position to find out what the specific volume is. And because we know what the specific volume is, we can find out the total volume also, no problem. V total also we can find out because we know the mass. The mass is known, so we can find out the total volume. But regardless, once we know the specific volume, we know that V2 will be half of V1. So over here, V2 is equal to V1 over 2. And so we are at a junction where we precisely know what the second point is. Okay. We know precisely what the second point is. So now the question says that what is the question? Until it reaches half the volume. Okay, so the question framing says that when it reaches half the volume, then it then starts cooling to 25 degrees Celsius. Okay, so it has reached half the volume over here, after which it goes to 25 degrees Celsius. So let me draw the 25 degrees Celsius isotherm. This is the 25 degrees Celsius isotherm, and it starts cooling. And once the piston reaches this point, and you're taking it to a lower sort of temperature, because there is no more movement of the piston, this is only the volume that you're playing with, the specific volume will remain constant. Okay, so that is why it's gonna be vertically straight line.
So,
Yeah.
so actually, the second step, like when it reaches the half initial value, and we don't know whether the piston is at.
No, so it is given in the problem that that is where the stops are. In the problem it is said, and it stops. Piston stops.
Okay, sir.
Okay. So then it starts going to 25 degrees Celsius. So now let us try to find out all the different states. Okay. So what do we have? So state 1. Okay, let's try to do it a bit more organized. State 1. The pressure is 1000 kPa. The temperature is 500 degrees Celsius. So let us find out the specific volume. We will quickly do it with EES first, and then we'll do it with the help of the tables as well. One moment. So let me share the entire screen. Okay, let me know if the screen is visible.
Yes, sir.
Yes, sir.
Yes, sir.
So the first point, so P1 is at 1000 kilopascal. P1 is 500 degrees Celsius. So let us first fetch what the specific volume is. So it's the volume, water, steam, T equal to T1, P, P equal to P1. Let's see what the specific volume is. It comes out to be 0.3541. Fine. So the specific volume is 0.3541. Now in state 2, we know that the specific volume of point 2 will be half of this. So it will be 0.172. Let's call it 0.1720. So we'll just say over here that V2 is going to be V1 over 2. All right, and P2 is going to be the same as P1. Why? Because the force is constant, so it's also gonna be 1000 kp. So in that case, let's find out what the temperature is. So let's say T2 is temperature steam P equal to P2, V equal to V2. So the second point temperature comes out to be 179.9 degrees Celsius. So this is 179.9. So if I were to draw an isotherm which passes through 2, passes through to point 2. So this isotherm will have a temperature of 179.9 degrees Celsius. Okay. Now what's the deal? Now we can say that V3 is going to be V2. T3 is going to be how much? T3
So 25.
25.
is 25 degrees Celsius. So let's correspondingly find what P3 is going to be. So P3 is going to be pressure, steam, T equal to T3 and V equal to V3. So let's see what it is. So P3 comes out to be 3.169 kilopascal. That's a very low pressure, but that is in fact the correct answer. So at state 3, P3 comes out to be 3.169, was it? Yes. Okay, so we now have all the state points. So now let us find out the work done. So what is the total work done? The total work done will be work in process 1, 2 plus work in process 2, 3. Now 1, 2, work during 1, 2. It's gonna be mass times the specific work 1, 2, and this is going to be mass times. So now in process 1 to 2, it's a constant pressure, constant force, meaning constant pressure process. So it's going to be the pressure at point 1 times the specific volume at 2 minus the specific volume at 1. Okay, and the amount of mass this has is 0.1 kg of water. So this will be 0.1 times 1000 kilopascal times V2 is 0.1720 minus 0.3541. And look, this unit is kilopascal, this unit is kg, this unit is meter cube per kg. So kg cancel, so it's the unit of this will be kilopascal meter cubed, and this essentially is kilojoule. Okay, this, when you multiply these units, you will directly obtain the answer in kilojoule. Okay, so how much is this? So let's write it down. W12 is the mass, which is 0.1 times P1 times V2 minus V1. So work during process 1 to 2 is minus of 17.7 kilojoule. And what does it mean? So this is minus 17.7 kilojoule. So what does it imply? That work is being done on the system. This implies work is done on the system. And that should be clear, because you are actually applying force on this to reduce the volume. So you're doing work on the system, and that is why it comes out to be negative. All right. Hey, so what is the work during the process 2 to 3?
0.
0.
It's gonna be 0 because there is no change in volume. All right. So this particular work done will be equal to 0. And so this is the final answer. So when such a question is asked to you in the exam, you should draw the final answer you should mark the final answer like this. Uh, you should also mark the final pressure. I mean, I'm marking it over here, but you should write down the desired things at a separate location and say that these are the answers. And you must be able to draw this to a very neat extent, to the best of your ability. Okay, you must try to draw it to the best of your ability.
Hello, sir.
Yeah.
So here we are not sure that the point two will be in the saturation region or not. So if asked in the
Oh,
exam, then
okay, okay,
then
okay, okay.
then
No, no,
we
no,
should
no, no.
write it.
Good, good, good. So thanks for asking that. So we are not sure whether point two is in the saturation region. Actually, yes, you need to find it out. So I could have done two things over here, but you should do the other thing. So the first thing, which you should probably not do, is to directly plot all the points. I go to property plot. Let me, let me just maximize this. I go to plots, property plots. I'll go to the PV diagram. Forget about these things, and I will plot t equal to t1. I will say t equal to t2, and I will say t equal to t3. Right? I will do this plots, and this is to be for steam. Oh, come on, I need to enter them again, is it? Oh man. Whew. That, well, okay. Why do they flush the buffers? Okay, we have these temperatures. We say, okay, okay, it doesn't accept these, so I will say 500, 169 point, what was it, 1? And what was this, 25? Okay, good. I say okay, no problem. So I have these three isotherms, and I will go to plots. I will go to overlay plots. On the x-axis, I have the pressure. All right. On the x-axis, I have the specific volume. On the y-axis, I have the pressure. All right. I click on OK, and this is how the process looks like. And if you look into the process, it does go into the second region. And but you see that the quality is very close to that being that of vapor. So in that case we should also verify that. So we should fetch what x2 is. So x2 will be quality of this same state. So let's see what it yields, and it gives us 0.91. So we're in the green. Okay, so this is what you should do. You should find out the quality, and then accordingly you can prepare the plot. But if you have a plotter ready for you like this, you can simply plot it and say, look, it's inside the dome. You can simply say it's superheated vapor. It's in the saturated dome. But in reality, you need to find out the quality of steam at this condition. So let me see, let me open Sontag, and let us try to fetch the values. Okay, I'm gonna get a copyright strike for this. What is this? Ideal gas properties. So we go to steam, saturated water. And so let's take stock. Okay, so forget this ever happened. I have no space to keep my stuff. So state 1, so the pressure, temperature, volume. So 1000 kPa, 500 degrees Celsius. So we should look at what happens at 1000 kilopascal and 500 degrees Celsius. So, okay, someone is writing something in chat, is it? No. No. At 500, so let's go to the superheated tables first. I'll tell you why. I'll tell you how you go about it. So we're in the superheated water vapor. Let me zoom out a bit. Let me zoom out a bit. So we are in superheated water vapor, and first of all, we will go to the 1000 kilopascal entry. So this is the 1000 kilopascal entry. So what do we see over here? So this is first of all superheated water vapor, and we are in the 1000 kilopascal. So let me snip it. So in the 1000 kilopascal, this is the 1000 kilopascal for superheated vapor.
So the temperature didn't come.
The temperature. Oh, sorry. My bad. So we need to drag it all the way from here. Now the temperature is there. So what do you see? So we first of all we see that uh, at 1000 kilopascal, the first thing that should strike you is that the saturation temperature, which corresponds to 1000 kilopascal, is 179.91. Meaning, if I were to draw the plot, so this is P, this is V. So if this is 1000 kilopascal, so this entire line is 1000. So the isotherm that passes through here, so this isotherm is 179.91 degrees Celsius. But our temperature is given to be 500 degrees Celsius. So this is the 500 degrees Celsius isotherm. And so this is the initial point. So this is point 1. All right. So point 1 is somewhere over here, because we see in the table that yes, indeed, the 500 degrees Celsius point is somewhere in the superheated zone. And which entry is which? So the first entry is the specific volume entry. First entry is the specific volume entry. All right. So the specific volume is this. So we will happily write down 0.35411. Okay. So we will happily write this. State 2 is at same pressure. Temperature is not known and the volume is half. So this is 0.17205. Okay. So now we are faced with a condition where the pressure is 1000 kilopascal. The specific volume is half of what we had and the temperature is not known. Now here is the tricky part. I mean, I'm saying a tricky part, but at saturation at 1000 kilopascal, the specific volume is 0.19444. So what does that mean? At 1000 kilopascal, when you are just at this point, this is the saturation point, meaning saturated vapor. When you are looking up the superheated vapor table, this point is going to be the first entry. I've mentioned this many times before as well. So this volume is 0.19444, but the volume that we see over here is 0.17205. So the volume is somewhere over here. This volume is 0.17205. What does it mean? We are in the saturated dome. So what do? We will now go into the saturated dome entries. So this was the superheated vapor table, vapor data. So we're done with this. Now we will go to, yeah.
So for 1000 kilopascal and the saturation temperature, the V is the Vg, or like in the superheated table.
In the superheated table, you mean this? It's
Yes,
obviously going to be the gas phase. See, superheated data, I don't know, I mean, so weird time to ask this question, but
okay, I understood.
superheated data is this data. So obviously the person who has made the table is first going to give you which data. He's not going to give you this data. That would be dumb on his part. He's gonna give you this data. Okay, so it's gonna be the gas part. Okay.
Yes, sir.
All right. So now we are in the saturated water pressure entry. This is the dome data. So in the dome data, we look for 1000 kilopascal. So it's over here. So let me take a screenshot. Copy. Okay, so now we have the data set in front of us, and 1000, this is the data under question. So what do? We know that at 1000 kPa, the saturation temperature is 179.91, and we knew this from before as well. And so Vf, so we will say that V2 is equal to Vf plus X2 into Vfg. So this is equal to 0.00121127 plus X2 multiplied by 0.19332, and V2 is equal to 0.17205. So X2 is 0.17205 minus 0.001127 over 0.19332. So who has a calculator handy?
So 0.8841.
0.88. Well, the book doesn't even tell the answer. So let's do it. So what is it? 0.17205 minus 0.001127. This divided by 0.19332. So 0.8841. So this comes out to be 0.8841. So okay. So what is the temperature going to be? At this point, what is the temperature? So we know that X2 is 0.8849. What is temperature? Look, we're in the dome. We're in the dome. So at this point, what should be the temperature? At this point,
Saturate.
saturation temperature. So it's 179.9. What kind of answers did we get? We got 179.9 only. Okay. Is that fine?
Yes, sir.
Yes, sir.
So this is how you need to approach the problem. You cannot just say that this has not been taught. It's only a question of logic, and I'm sure all of you are very solid in logic. You are better than me in all this kind of stuff. It's just that there's going to be a mental block because some senior told you that this is a killer subject. That's wrong. If you start enjoying this, it's good. All right, point three. Point three is 3.169. That is the final answer. It's 25 degrees Celsius. Okay, so then the thing is cooled to 25 degrees Celsius, and we have the same specific volume. 25 degrees Celsius, same specific volume. So what should I do? I should go to this. I will go to, instead of pressure entries, what entry should I look at?
Temperature entry.
I should look at temperature entry because it's 25. It's a good number for temperature to be at. So I will go to saturated water, 25 degrees Celsius. Where is it? It's over here, but this is the enthalpy entropy page. Specific volume, 25 degrees Celsius. There we have. All right. So I'm going to take a screenshot. 25 degrees Celsius. All right. So at 25 degrees Celsius, the question is, how much is the pressure? And let's see, how do we find the pressure? I mean, the logic behind it. So 25 degrees Celsius, you will be tempted to directly say, oh, here I have it. I mean, the pressure is 3.169, but no, because you know that the specific volume at this point, at point 3, is also 0.17205. You must first ascertain, first see whether 3 is inside dome. So V3 lies between Vf and Vg. Yes? Does it? V3, it lies between Vf and Vg. Yes, it does lie between Vf and Vg. So we can conclude, yes, it is inside the dome. And so, corresponding to a temperature of 25 degrees Celsius, the pressure is therefore going to be the saturation pressure at that temperature. Meaning, in the plot, this is the 25 degrees Celsius isotherm, and the pressure corresponds to the saturation pressure at this temperature. So this is 3.169 kilopascal. Okay. So this is how you would solve the problem. This is 3.169. The rest of the calculations are quite straightforward, meaning the work done calculations are quite straightforward. Is that okay? Does everyone understand?
Yes.
Now, who will tell? Not Anirudh Bajaj, not Adarsh Sharma, not Daivik. Someone else will answer. G Chetan, you there? G Chetan. And not even, so that guy is not present today, is it? I keep forgetting his name. South Indian guy. Sai Venkat, no, what is his name?
Gande Venkat Sharan.
It's a bit complicated. It's like VVS Lakshman. He's not there. He's unwell, is it? No. Maybe he'll look at the. Who will answer? Tushar Punia, are you there at least?
Yes, sir.
So let's do this. The entire problem we will now try to plot in the TV diagram. T versus V diagram. This also is a very important skill. You cannot do without this. You must be able to draw the schematics on the TV diagram as well. So on the TV diagram, first thing, Tushar, what should I do?
One second, sir. Can we see the processes, sir?
I will tell you the processes. Process 1, 2, 3. 1000 kilopascal, 500 degrees Celsius, then volume becomes half volume and pressure is 1000 kilopascal. Then third process is 25 degrees Celsius, specific volume remains the same. This is the process.
Yes, sir.
So how do I draw the process 1 to 2?
Yes, sir. Pressure.
First
The
thing,
first
what
is,
should I draw? Very first thing, I should draw something on this plot. What should I draw?
sir, that 1000 kilopascal isobaric process.
Yes, very good. You are correct. See, why are you nervous? Don't be nervous. So I will first draw the 1000 kilopascal isobar. You are correct.
Yes,
Don't
sir.
be nervous. 1000 kilopascal isobar. On this isobar, how will I identify where point 1 will be? Point 1.
Yes, sir. So I will try to find
No,
the
Tushar, first of all, what is this temperature, Tushar? We have
this is
already
five.
found.
It's a 500 degrees Celsius.
No. This is not 500 degrees Celsius. This temperature corresponds to the
It
saturation
says
temperature.
at 1000 kilopascal.
So
T
what
said
is that? We have just found it out. It comes out to be
170.
very good. So this is 179.91 degrees Celsius. So correspondingly 500 degrees Celsius will be somewhere over here, right, Tushar?
Yes, sir. Above. So it
So
will
we
be in
will,
per rate reason.
so this is point 1.
Yes, sir.
Now where is point 2?
It's a point two is in domain that.
Inside the
Sorry.
dome, inside the
Yes, sir.
dome it is. So that the volume is half its volume. So this is V2 by 2. It is somewhere over here, inside the
Yes.
dome. And point 3, where will the process go? Point 3.
half to the original, this half of this
No,
volume.
this is already done. This is already halved. Point 0.3 is not volume halving process.
No, sir, it is constant. So we have to
What we
make
will draw? Isochoric.
isochoric process.
Very good. So it will go like this. This will be 0.3. Yes?
Yes, sir.
Very good. So Tushar has answered it. I mean, I am not sure why I am surprised, but Tushar has answered it. This is the process. So 1, 2, 3. Tushar, correct?
Yes, sir.
Everyone, not just Tushar, everyone must understand how to draw this as well. Otherwise, you will be caught out by a googly. Okay, you must know how to draw it on a TV diagram as well. Alright, very good, Tushar. It's 10 o'clock. Let's take a small tea break. And when we come back, we will start with the first law. Okay? So don't go anywhere. I'll be right back.
So one typo is there, sir.
Huh? Huh?
So one typo is there. It's V1 by 2.
Oh, sorry. Well, I wouldn't call it a typo, but this is a. I mean, I was just seeing whether you're attentive. So clearly you are attentive.
So before that too, we took as a specific volume of V2 as something else. It should be 0.17705.
Or it should be. Ah, yes, yes, yes. Oh, this was incorrect. Come on.
Yes, sir.
Wow. I did not expect myself to make the mistake. Okay. Thanks. Thanks for pointing it out. So, in the meantime, you just find this out. It should be 0.91 something, right?
Yes, sir, it is 0.908.
Good, good. So this was incorrect because, I mean, my sketchy mental math has confounded me. Yes, my sketchy mental math has confounded me. So thanks for pointing it out. So you can safely assume I was just trying to see your attentiveness, but yes, in this case I do agree I was wrong. So I'll be back. So I will keep the recording on, no problem. So Okay, we're back. So let's proceed. So I'm gonna save this file and I'm gonna create a new file. So let me share the screen as well.
So,
Yeah.
sir, in TV diagram between the process first and second, how can we say that there is a straight line?
No, we cannot say it's a straight line. It's an isobar.
Oh, yes, sir.
Isobar is curved slightly. Slightly, yeah.
Okay, sir.
So if you have doubts, you can go here. You can go to plot, property plot. For steam, you go to TV diagram. We will not include any isentropic lines. We will say pressure. I want 1000.
Sir, I am not able
The
to see ES.
ES screen is not.
Sir, you
Oh,
cannot
sorry,
share
sorry,
full
sorry.
screen.
I have to share my entire screen. Now, okay, I'll do it again. We'll go to
Sir,
plots, property plot, steam, TV diagram. We don't want to include this. We will include pressure of 1000 and pressure of 3 point, what was it? 169, right? We go to OK. Now in this plot, we will go to plots, overlay plot. On the x-axis, we have the specific volume. On the y-axis, we have the pressure. We click on OK. What happened?
Sir, on y-axis, it's temperature.
Oh, sorry. If you go to plots, overlay plot, on the y-axis, we have the temperature. Okay. So forget about this line. How do you actually modify? So I will get rid of this. Delete. Okay. Yeah, good. So this is how the process looks like. The lines are not straight. If you notice, they are slightly curved. Okay.
yes, sir.
And actually the point, I mean, see, ES does not know that we did an isobaric process. So this point to this point, it will not go in a straight line. MS, your name is, I don't know what your name is.
Yes, sir.
Your name is Manish. So Manish, this is not correct. The actual process will go along this isobar. It will go to this point, then straight. Okay. It
Yes,
will
sir.
not go in this because ES does not know. It has simply plotted it like that. Okay. This much should be clear to everyone. All right. Close this. Stop sharing the entire screen. Only share this journal. Okay. So we're done with chapter 4. We've now transitioned to chapter 5, which is the first law. Okay. So the first law of thermodynamics, we will start with a control mass approach. So this particular chapter, that is chapter 5, will deal exclusively with analysis of control masses. So what do we mean by control mass? It's something like this, which is the identity of the mass is going to be fixed always. There is no flow coming in, no flow going out. Okay, there will be no flow coming in, no flow going out. And a very simple thought experiment is as follows. So there's a small impeller like this, and it's connected to a pulley, and this is connected to a mass. Okay, so the control mass in this case is whatever the gas is inside this chamber. Now let's imagine that this gas undergoes two processes. So in the first process, say the mass goes down. So when the mass goes down, so mass goes down, So what does it mean? The impeller turns. So what does that mean? You're doing work on the system. And you can imagine, because there's going to be some churning going on, the temperature increases. Okay, so temperature increases. Then because the temperature is increased, you want to go back to the original state. So state 2 is at a slightly higher temperature, same specific volume but slightly higher temperature. So then you remove heat to go back to state 1. Okay, so in going from state 1, in going from state 1 to 2 and going from 2 to 1, you have thus done a cyclic process. You have done a cyclic process where you did a certain amount of work and you removed a certain amount of heat. So it has been found historically that in this process, the total amount of heat transferred is proportional to the total amount of work done. Okay, this is the important point, because we are working in a cyclic process. We have the cyclic integrals, and the simplest cyclic process is what I have shown. You do some work on the system and then you remove heat to go back to state 1. So this has been historically found, and in SI units we say that del Q is exactly del W, and this is a statement of the conservation of, or the equivalence of, work and heat. Okay, this is the first important point. Now with this in mind, we can now go ahead and write down the first law for a change of state. So now with this in the background, we can write down the first law for the change of state of a control mass. So remember, we're dealing with control mass and we're dealing with cyclic process. So cyclic process, this is true. Now with this information, we're gonna try to derive something for a non-cyclic process as well. All right, so let me do the following construction. Let me do the following construction where we have state 1, state 2, and PV doesn't matter. So we can have one cycle which looks something like this. That is, we go from point 1 to point 2 using a process A, right? And we come back to state 1 using process B. Now we can imagine another way of doing it. So process A, process B are non-unique. Meaning I could have gone from point 1 to point 2 in any manner. I could have done this also. I could have done this also. I could have gone in any way. In fact, a very pragmatic way would be isochoric heating. I could go isochoric heating like this and then isobaric expansion like this. This is also valid. No problem. But the important point that I'm trying to make is that point A, rather the processes, process A and B, they are non-unique. So I could equivalently have another process, this. I can go from point A1 to point B in process C and come back to process to state 1 through process B. So I have now two sets of processes. One is 1 to 2 using A and 2 to 1 using B, and I have 1 to 2 using process C and 2 to 1 using process B. And because this is going to be valid, for the first process, I can write del Q del W, and in process A, I can split this as integral del Q going from 1 to 2 plus 2 to 1 del Q, and this is going to be equal to del W 1 to 2 plus 2 to 1 del W. I can obviously write this because cyclic integral is nothing but splitting of these two integrals, and I will put subscripts A, A and B, B, because 1 to 2, whatever heat transfer is taking place is during the process A. 2 to 1, whatever heat transfer is taking place is through process B. 1 to 2, whatever work done is happening is due to process A. 2 to 1, whatever work done is due to process B. So far so good? Is that fine? Is this okay to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Well, now I can simply write the same formula for process CB, meaning I go from state 1 to state 2 using process C, and I go from state 2 to state 1 using process B. So here I can simply write C, the other process still remains B. Okay, so this process yields this equation while this process yields this equation. Now what can I do? I can simply subtract these two equations. So subtracting, I will obtain 1 to 2 del Q A minus 1 to 2 del Q C. This will be equal to 1 to 2 del W del WA plus 1 to 2 rather minus 1 to 2 del W C. Let me rearrange the terms. So I have 1 to 2 del Q A minus del W A is equal to 1 to 2 del Q C minus del W C. And this is quite profound in the sense that it says that in going from process 1 to 2, the work done and the heat transfers are obviously different. In going from 1 to 2, you have process A, process C. Del Q A is not equal to del Q C. Del W A is not equal to del W C. But the difference of del Q A and del W A is equal to del Q C and del W C. And how can I get rid of the integral sign? Well, I can simply say that A and C can be anything arbitrary. Because A and C can be arbitrary, if these two integrals are to be equal, then the integrands also have to be equal. Okay, someone may think that no, this integral is equal, meaning the area under this curve and the area under this curve can be equal. And this is not equal. But no, this is true for any arbitrary process A and any arbitrary process C, and this equality can therefore only hold true when the integrands themselves are equal. Alright, so we define a parameter called as the energy of the system, that is going to be dE. and we will say that DEA equal to DEC. It is the total energy content of the system. Total energy content in system. It is not just the internal energy, we will come to that. So what is the important takeaway from this? That Q and W are path functions, but Q minus W is a state function. This is a very important conclusion of this. Okay. So essentially we can then write dE is equal to del Q minus del W, or equivalently E2 minus E1 is equal to del Q in going from process 1 to 2 minus del W in going from 1 to 2, where well, this will not be del anymore, where each of these terms individually depends on the path. Each term depends on path individually. But the change in total energy does not depend on the path. Okay. So this is the statement of the conservation of energy, and this comprises the first law for a control mass. This is the first law for control mass. Now what does E comprise of? E is comprised of three things. First is the internal energy. Second is kinetic energy. The third one is the potential energy. Let us discuss each of these three terms: internal energy, kinetic energy, and potential energy. Internal energy is the energy manifested due to microscopic motion of atoms or molecules in system. Okay, so all the statistical mechanics ideas go over here, and with the help of that you are able to determine the internal energy. So it is literally the ensemble average of the kinetic energy of the molecule, the number of collisions that happening, and so on. So this is happening at a microscopic scale. Okay, meaning that if the amount of collisions and vibrations of the molecules increases, we say that the temperature has increased, and the temperature increase that you perceive as something measurable is basically nothing but a statement which says that the internal energy has also increased. So if you add heat to a system, if you give heat to a system, right, then you are essentially causing the internal energy to go up. And a consequence of the internal energy going up is that the number of collisions between the particles, the velocity, RMS velocity of each molecule or atom has also increased, and the temperature also increases. Okay. Now similarly, kinetic energy. So say you have a block like this, and you do work on the system. So this is your system, you have a block, nothing else. So when you do work on the system, what is the sign of W12? Work done on the system.
Negative.
So when you do work done
Negative.
on the, so when you do work on the system, so W12 is negative. So if you look over here, the right hand side is positive. Suppose there is no heat transfer. So RHS is minus W12, but W12 will be negative. So this quantity is essentially positive. So it will lead to a change in energy of the system, meaning this solid block will start moving with some velocity. So the kinetic energy is what? Half mv square. This velocity is the microscopic velocity, is the velocity of the block. This has nothing to do with the RMS velocity of the molecules. Okay. Similarly, what about potential energy? Say you have a block, you do work on the system, and suppose by doing work on the system you are able to lift this mass. Then what does it mean? Just give me a moment. Alright, sorry about that. So the mass is lifted, and essentially you have an increase in potential energy. So when you were doing work on the system, once again the minus W12 quantity will be positive, and therefore you have increased the energy of the system. Is that fine? Any doubt so far? Any doubt so far?
Yes, sir.
All right. So I have told you that you have done work, but you may say, wait, what about heat? I mean, heat increasing the energy, internal energy is obvious, but let's see how we can have a system where adding heat is tantamount to maybe increasing potential energy. I'll just give you the potential energy stuff. You can figure out the kinetic energy as well. So suppose you have a cylinder piston arrangement like this, and there is some mass over here, and this cylinder is connected to another volume like this, and this volume it contains water. This volume it contains water, and you're heating it from the bottom. So when you heat the system, so if you consider this as the control mass, when you consider this as the control mass, okay, then what happens? Addition of heat causes the pressure to rise, and so this mass will effectively be lifted. This mass is effectively lifted, so addition of heat is also tantamount to increase in potential energy. So if you look at this equation, E2 minus E1 is equal to Q12 minus W12. So over here, okay, you are adding heat. At the same time, there is some amount of work done by the system as well, and the deficit of this will be manifested as the change in. So over here, because we are concerned with the change in energy of the block, we must also account for the block in the control mass. We must also account for the block in the control mass. Okay, so you have essentially changed the energy of the system. All right, so I mean, these problems are very easy problems, and we're not gonna deal so much with this. I'll give you some examples to do. They're really simple, they're not at all difficult questions. I mean, they'll feel easier than JE questions. So internal energy is the main property that concerns us in our study of thermodynamics. And internal energy is a thermodynamic property. So now we are going beyond pressure, volume, and temperature, and we are trying to bring in more properties. And uh, you have already seen that. Let me take a screenshot. You've already seen in the tables many times that this internal energy is also listed as a table, meaning you can also specify the state by using internal energy. Temperature is always there, specific volume is always there, temperature, pressure, these three we have dealt with. But you will see in the tables that internal energy is always there listed, meaning you can determine the state using internal energy as well, meaning temperature and internal energy can be a pair, or the specific volume and internal energy can be a pair, or the pressure and internal energy can also be a pair. What are the other properties that you have seen in the table? Some other properties that you might have come across, stumbled across?
So enthalpy.
Enthalpy and entropy.
Enthalpy and entropy, as we will see in the later chapters, they are also thermodynamic properties. Okay, so we denote internal energy by the symbol U. Total internal energy will be U. Specific internal energy will be small u, which is the capital U over the mass of the system. Okay, and yeah, U is is an intrinsic property of the system. So why do we say that E is not the thermodynamic property? E is not the thermodynamic property because you have the kinetic energy and the kinetic energy, the potential energy, and you have half mv square. Okay, so you sort of abstract a system with its mechanics. So this follows from how the dynamics of the system works. You have a mass which moves with a volume, so it has half mv square. But even when the mass is not moving, when the potential energy has not changed, and a system, by the sole virtue of its molecular interactions inside the system, it has a certain amount of energy, and that is intrinsic to the system. So it is an intrinsic property. It does not depend on the mass. Specific property, specific internal energy. It does not depend on the mass, and we will say that it is an intensive property. It is not only an intensive property, but it is also an intrinsic property, meaning it is inherent to a system. Because of the molecular interactions, the atomic interactions, it is intrinsic to a system. It does not depend whether it is sitting on top of a mountain, or whether it is sitting at sea level, whether it is moving with a very high velocity, or whether it is not moving at all. It is the intrinsic property, and hence we can treat internal energy as as a thermodynamic property. It is also an intensive property because it does not depend on the mass. You can take a small chunk of it, it will have the same specific internal energy. You can take the entire system, it will also have the same amount of specific internal energy. Now, this is fine, but how do we find out the total internal energy of a liquid vapor system? Liquid vapor dome. Inside the saturation dome, how do we find the total internal energy? So we can write the total internal energy capital U as capital U for the liquid plus capital U for the vapor. Okay, this U looks like a V. Yeah, much better. So the total energy, internal energy, is equal to the specific internal energy times the mass of the system, right? So we can do this. So we can say mass times the specific internal energy of the system, and this is equal to the mass of the liquid times the internal energy of the liquid. So UF, if you look over here, saturated liquid, it is denoted by UF, and U vapor, which is M of the vapor times U of the vapor, which is denoted by UG. Okay, so now we can divide everything by mass. So you have U is equal to M liquid UF over the total mass plus M vapor over total mass times U of the gas. What have we defined already as M liquid over M? We have defined this already. We have used it in fact to solve problems.
1 minus x.
1 minus quality.
So it is going to be 1 minus quality, whereas the quality is defined as m vapor over the total mass. Okay, these two definitions we will use now. So this is 1 minus the quality times uf plus quality times ug. So this becomes uf plus x times ug minus uf, and this becomes uf plus x ufg. So what this means is the internal energy inside the saturated dome is given by a very similar formula that we had for the specific volume, because specific volume was also Vf plus x Vfg. So because Ufg is important, it is also listed in the tables. It is also listed in the tables. Okay, so far so good. Let us do a quick example. Let us do a quick example to drive home the point. So let's say, so question, find out the specific internal energy U, specific internal energy, find out the specific internal energy U of steam at a pressure of 0.6 megapascal and a quality of 95%, and 95% is equal to 0.95. So let me share my entire screen. So I'm gonna share the entire screen. So let's go to thermodynamic properties of water. What is asked is 0.6 megapascal and a quality of 0.95. So let's go over here. Is the entire screen visible?
Yes, sir.
Yes, sir.
Okay. So this is the saturated water property and this is the temperature entry. But because we have been given the pressure, we will go to the pressure entries. So let's go there. So we are now at the pressure entry. So what is the pressure? 0.6 megapascal, that is 600 kilopascal. So this is 600 kilopascal. So let me take a screenshot. Take a screenshot and dump it over here. Okay, so 600 megapascal. So let me just grab this question over here also. So what do we have? So pressure 600 kPa. I mean, is this visible or is it too small? Okay, I mean, you can download it and look at it later. So 600 kilopascal, these are the entries of our interest. So how much will be the specific internal energy? U will be UF plus 0.95 UFG, which is 669.88 plus 0.95 times UFG. So this is the UFG entry. UFG over here is 1897.52. 1897.52. So what does this come out to be?
So 2472.12.
2472.
Okay, my calculator has completely gone. Is this? Can I get a better calculator? Like scientifically. Let's see. 669.88 plus 0.95. Oh, there's no bracket. That is why. So I'll do this. Where is this AC button? Oh, C. Clear. 0.95 times 1897.52 plus 669.88. 2472.5 2472.52. So what will be the units? It will be kilojoule per kg. So it's the energy per unit mass. This is specific internal energy. And so let's also do it in ES. So let's also do it over here. So you can say U1 is equal to int energy steam P equal to 600, X equal to 0.95. 2472. Okay. Fine. So this is how you fetch the values. Okay, so let's do another problem. Let's do another problem to drive home the message. So the question is to find out for steam, we must find out all the missing properties. So question 1, temperature is 300 degrees Celsius and the internal energy is 2780 kilojoule per kg. So we must find out all the other missing quantities. So let's see at 300 degrees Celsius. So first of all, our task will be to determine. So this is a very, important concept. The first task will be, is the state superheated or is the state in saturated dome? So let's see, at 300 degrees Celsius we will go to steam. So at so we will go to temperature entries because we have been given the temperature. So this is the table for saturated water at 300 degrees Celsius. This is what we have. Let me take a screenshot for everyone's benefit. So at 300 degrees Celsius, what do we observe? At 300 degrees Celsius, this is the internal energy data. So what do we observe? What is our observation? That at 300 degrees Celsius, the specific internal energy of the vapor is 2562.96, which is less than what we have. It means that the state is at a higher energy than the saturated vapor. What does it imply, everyone?
It is in superheated region.
So this
Superheated.
automatically implies that the state is in superheated region. So fine, let's do that. We go to the table again. Now we must scroll to the superheated vapor. And what have we been given? T equal to 300 degrees Celsius. Okay. So how do you quickly do it? The way is simple. At 300 degrees Celsius, the saturation pressure is 8581. So we definitely know that we have to look for a pressure higher than 8581. So we will go over here. No. What did I? At 300 degrees Celsius.
I think yes, so we have to look for 8581 or more.
Yeah, that is fine. Yeah, fine. Let's see. 8581. So basically we have to go for a table which will give you a temperature more than 300 degrees Celsius at saturation. So we're looking at superheated water vapor. We will look at the brackets. So this bracket says 170. These are the temperatures. So we will have to definitely go beyond 300. 300, where is 300? So at 10,000 kilopascal, we have the first entry of 311. Okay. At 10,000 kilopascal, we have the first entry, and I mean, is the question right? I mean, such a high pressure. So let's look at the internal energies over here. So the internal energies, the one that we want is 2780 kilojoule per kg. So what will we do is we will take a screenshot of this. Put it over here. Let's also grab our problem. Over here. So this is what we desire. And 300 degrees Celsius, 2780, 300. Okay, so I mean, this problem is probably not a very well framed problem, because you see at 300 degrees Celsius, the internal energy is very close to 2780 over here. But the entries over here, I mean, you have to interpolate first to find out a pressure at some intermediate, I mean the saturated values at some superheated values at some intermediate region. This is probably not a well framed problem to do using a table. We'll quickly do it using ES first. So P equal to pressure, steam, P equal to 300, U equal to 2780. Solve this. So the pressure comes out to be 1618. What's going on over here? What seems to be going on? Anyway, we're also out of time. So next class we will start with this problem once again. Okay. So it's between these 2 points. Anyway, we'll do this again. Forget this happened. Otherwise, it will cause more confusion than anything. Okay. So next class we will start with these problems once again. And yeah. In the meantime, I'll send out some practice problems, which you should also start doing. So this will be practice problems from chapters 3 and 4. And you should start doing them with both. I mean, you should start conceptualizing them and solve it using ES and table both, so that you're well conversed with both the techniques. Okay. So I'm going to turn off recording now.